All right, let's take a look at Unit 7, Lesson 7, areas under a normal curve. So we're going to take a look at the normal distribution and use it to estimate the proportion of data values falling within given intervals. So in 7.1, the images show a normal curve with a mean of 40 and the standard deviation of 2. And they show you that the area under the curve to the left of 39 is 0.3085. So about almost 31% of the data is under the curve to the left of 39. And then on the other curve, on the other diagram, the area under the curve to the left of 43 is 0.9332. So about 93% of the data is to the left or is less than 43. All right, so find the area under the curve to the right. So now we're looking at this side. Well, remember that the whole area is 1. So 1 minus that 0.3085 would give us 0.6915. So that would be the area to the right of the curve, to the right of 39. And then we want to find the area under the curve between 39, so that would be like right here, and 43. So we're trying to find this area here. Well, if we know that the area for 43 to the right of to the left of 43 is 0.9332, and we were to take away this area, which is right here, then we'd be left with what is blue. So we're going to subtract that 0.3085, and that will give us what's left underneath, and that would be 0.6247. And you could just use a calculator to find that. All right, then we want the area under the curve to the left of 40. Oh, excuse me. To the left of 40. So keep in mind that 40 is right here, and this is a normal curve, and 40 is the mean. That is the it's also the median, right? So 50% is going to be to the left, or 0.5, because 40 is the center. So half of the data would be to the left, and half of it would be to the right. All right, and then find the area under the curve between 39 and 40. Well, if we know that to the left of 40 is 0.5, and we take away what's to the left of 39, we end up with what's in between, which would be this area, and that would be 0.1915. So that's how you can find different areas under the curve once you have certain numbers that are given to you. All right, so taking a look at the second part of the lesson, life of lights. The lifespan of light bulbs is approximately normally distributed. Some statistics about lifespans of 2 different light bulbs are listed. So with LED bulbs, we have a mean of 2,300 days and a standard deviation of 230 days. And then for incandescent bulbs, we have a mean of 100 days and a standard deviation of 10 days. So LED bulbs tend to last longer, a whole lot longer than incandescent. All right, so we are going to estimate the proportions of bulbs that burn out in a certain interval of time, and we're going to use Desmos to help us. All right, so first, we are going to pull up Desmos. We'll split our screen with that. And then, so for the first one, we are going to estimate the proportion of LED bulbs that are expected. So we're going to talk about LED, and we're actually going to do all of the LED bulbs first, because that's all part of the same distribution. So we're doing a normal distribution. Our mean is 2,300. And our standard deviation is 230, right? And I'm going to tap on that little hourglass looking thing, not hourglass, magnifying glass. So that way we can actually see our curve. And then if we want to find the cumulative probability, that tells us the area under the curve. And so if we are looking at the proportion of LED bulbs, for number one, that are expected to burn out before getting within 1 standard deviation of the mean. So that's before 70 days. So our maximum is 2,070 days. And so we are looking at 0.1587. All right. Then we're going to skip to number 3 so that we can just keep using the same distribution. Although I wonder if we can, let's try this. We'll try putting them both on the same. That might make it hard though, because we might not be able to see them, but that's okay. We'll look and see if we can't work that out. All right. So this time it was 100 days for the mean for your, incandescent, and then 10 days for the standard deviation. And we'll do that, and we'll do that. All right, so again, when we put in the incandescent, and we're going from basically negative infinity because it goes off to the left forever, but it stops at 90 days, we have 0.1587. So for both of those, they would expect to burn out before getting 15.87% of the bulbs would be expected to burn out before getting within 1 standard deviation of the mean. All right, so now we're looking at them burning out after getting more than 1 standard deviation greater. So now our lower limit is 2,530. Oops. And our maximum, let's see, did we have infinity on here? It's not a function. I wonder. If I just type it in. There we go. If you type in infinity, it works. All right, and then we're going to look at that. Let's see. If I tap on that, if you tap on the magnifying glass, it takes you right to it. So that's nice. So now we can see, visually see, our lower limit is 2,530, and our upper limit is infinity. And again, we still get 0.1587 because we're within 1 standard deviation, but now we're looking at above that mean. All right, and then let's take a look at the other one, the incandescent. So now we're looking at after 110 days, which again is 1 standard deviation away from the mean. And so there is no infinity button, so we have to type in infinity and then it automatically changes it for us. And so that one is also 0.1587. All right, now we're going to estimate the proportion of LED bulbs. So we're back at the first one, the red one, that are expected to burn out in the interval between 1 standard deviation less than the mean and 1 standard deviation greater than the mean. So we're looking at between 2,070 and 2,530. And so there is your shaded region. And we can see that that is 0.6827, which makes sense with what we talked about in lesson 6. It's around 68% is within 1 standard deviation of the mean. So now we're going to take a look at the same thing for incandescent bulbs. And this time between 1 standard deviation away is 90 and then 110. Tap on that magnifying glass to see the diagram. And again, we get 0.6827. So that makes sense because we're within 1 standard deviation of the mean and on either side. So it's about 68% of the data or of the bulbs. All right, now we're taking a look at the proportion of LED bulbs, so we're back to the red one, that are expected to burn out in the interval between 2 standard deviations, less than the mean and then greater than the mean. So we're going 2 standard deviations away. So instead of 230 days away from 2,300, we're going 460 days on either side. And so 2,300 minus 460 is 1,840. And then 2,300 plus 460 is 2,760. And we'll tap on that magnifying glass so we can see the diagram. And we get 0.9545. So that's almost 90, that's around 95% of the bulbs would burn out within 2 standard deviations of that mean. All right, number 8, we're estimating the proportion between 1,900 days. So now we're not looking at a specific number of standard deviations. We're just looking at, some values, some number of days, right? And so for this one, if we're looking at between 1,900 days and 2,100 days, it's going to be 0.1513. So a little more than 15% of the bulbs would be expected to burn out between 1,900 days and 2,100 days. All right, and then for incandescent bulbs, for the last one, we're looking at the percentage or the proportion that we expect to burn out between 107 days and 118 days. And let's take a look at that. And that now we're above the mean, and it's 0.2060. So a little over 20% of the bulbs should burn out somewhere between 107 days and 118 days. So that's how you can use Desmos to help you find the proportions, whether you know how many standard deviations or not. 7.3 we are not going to worry about because it actually goes a little beyond what you need for this class because you're finding an interval that fits a certain percentage as opposed to finding the percentage that fits the interval like we just did. So that's a little bit more detailed. But if you do take a statistics class, you'll get into that. And then you have the summary here that you can read through if you want, but it just kind of reiterates how we can use Desmos or a graphing calculator like a TI-84 to figure out what the proportion is within a certain region when you have a normal distribution.